In the same way that we can represent the exponential function e to the x as a power series, we can represent e to the at as a power series where A is an n by n matrix. The power series expansion for e to the x is 1 plus x plus 1 half x squared plus 1 over 3 factorial x cubed and so on. And the way we find the matrix exponential, that's what this is called, is e to the at is the identity matrix plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial and so on. With that in mind, we have a matrix A, which is 0, 1, 1, 0, and we're going to find e to the at. And then after some theory, we're going to tie this into differential equations. E to the at starts out with the identity matrix, I'm not going to write that down yet, times at, and then we need powers of a squared, a cubed, and so on. And so that's what we're going to do our work here. We're going to write down a squared, which is 0, 1, 1, 0 times 0, 1, 1, 0. Multiplying these out, you're going to find that this is 1, 0, 0, 1, which happens to be the identity matrix. This is going to make multiplying pretty nice, but it's going to allow me to illustrate how we do our work here. A cubed is a squared times a, but since a squared is the identity matrix, a cubed turns out to be a. We can see that a to the fourth is going to be the identity matrix, a to the fifth reverts back to a, and so on. So e to the at is equal to the identity matrix 1, 0, 0, 1. We're using the 2 by 2 identity matrix because our matrix is 2 by 2. Plus a times t is 0, t, t, 0. Plus a squared t squared over 2 factorial. That's going to be t squared over 2, 0, 0, t squared over 2. A cubed times t cubed over 3 factorial is going to give us 0, 1, 6 t cubed, 1, 6 t cubed, 0. And this goes on infinitely far. It's an infinite series. I'll cut it off there and combine all these matrices into one big old matrix. Well, we can see in the upper left what we have is 1 plus 0 plus t squared over 2 plus 0. And you can probably guess the pattern from that. I'm going to write it down as 1 plus 1 half t squared plus 1 over 4 factorial t to the fourth, and so on. In the upper right corner, we have 0, t, 0, 1, 6 t cubed. So you can probably buy that this is going to be t plus 1 over 3 factorial t cubed plus 1 over 5 factorial t to the fifth, and so on. You'll also no doubt note that all of the lower left entries replicate the upper right entries, and all of the lower right entries replicate the upper left entries. What we have is a matrix that's got a bunch of infinite series in it. You may remember from second semester calculus that we have Maclaurin series, not just for e to the x, but for the cosine of x, the sine of x, the inverse tangent of x, and several other functions. Trying to match one or more of these up with what we just saw suggests that what we have in the upper left is a hyperbolic cosine. Well, it's upper left and lower right. And what we have in the upper right and lower left is a hyperbolic sine. So in this case, we have that e to the at is equal to the hyperbolic cosine of t, hyperbolic sine of t, hyperbolic sine of t, and a hyperbolic cosine of t. That's our e to the at. They don't always turn out nicely like this. And if you need to look up one of these forms, as far as I'm concerned, just look it up. But we were asked for e to the at and e to the negative at. E to the negative at just asks us to change the sign on t. The hyperbolic cosine had a bunch of even degree terms, so it has no change at all, but the hyperbolic sine had a bunch of odd degree terms. So e to the negative at is hyperbolic cosine of t, negative hyperbolic sine of t, negative hyperbolic sine of t, and hyperbolic cosine of t. That's it for that exercise. If you remember or look up identities related to the hyperbolic functions, then you can verify that e to the at times e to the negative at gives us the identity matrix. That's actually true in general because a times a commutes with itself. So if I multiply a by a, it doesn't matter in what order I write the a's. In general, a times b does not equal b times a when we multiply matrices. But if it happens that a and b are two matrices that do commute, so we can multiply them ab and ba and get the same result, then e to the a plus b is equal to e to the a times e to the b. In the case that AB does not equal BA, this equation does not work. But because A does commute with itself, we get, generally speaking, that e to the at, e to the negative at is e to the at minus at. That gives us e to the 0 matrix, which is the identity matrix. And so e to the negative at turns out to be the inverse of e to the at. That's a fact that's going to be useful before we're done with this set of videos.